Hello everyone, my name is Anirudh. In this video I will be explaining about entire multi-phase flow using cavitation method, and these everything setup and meshing as well as design is carried in CFD ANSYS software, that is ANSYS Fluent. So we will be covering this design in space clamp, the meshing, the meshing methods, as well as the refinement, the sizing, everything we are going to discuss in meshing. And the name sections also are covered in this meshing setup. And coming to the next part, that is setup for that is pre-processing everything for the CFD Fluent, that is setup. So in this we are going to set up the cavitation model, as well as we are going to use the pressure Python software for this Python Jupyter, and we are just going to convert the pressure units with the help of Python. So I will be explaining that also, and at the last we are going to compare the results. And before this video I uploaded one more video that was regarding cavitation problem. So yes, just go to that video and watch it, you will get a clear idea. So this is the geometry. The entire geometry is 2D. I included the guide veins just to make sure that every part of the bubbles are observed over this surface. And this is a simple 2D geometry, as well as I created this shape in such a manner that it acts as a venturimeter. So this will be my inlet. From here the inlet will pass, and entire surface will be covered with the air only, and because of pressure difference the air will go from inlet side to outlet side, because the outlet pressure is quite low and compared to the inlet. This is the venturi type design. This 13.09 mm which I wrote here, this entire section is throat, and here the major difference, that is pressure difference, occurs from high end to low end. These two are converging angles, and these are the diverging angles from where the air is going to split, and they are going to the outlet zone. This is the 60 mm guide veins. The entire setup was done in the space clamp software. So this is the annotation plane, just to show you this details of the dimensions. So coming to the next part, that is meshing. I will just skip this part of the run load time. So here this is the meshing. Yes, so coming to the meshing part, I completed the meshing. So the options, the methods which I have inserted is this face meshing. So here there is an option named as face meshing. So in face meshing I have selected this entire face from this option. Here the option will pop up with a plane, only one single surface, so that you can select, as it's 2D. So there will be no need to worry that how come this the whole body as well as the edges are hidden out. So yes, the face meshing with the 2D, I click save the face meshing. There will be the face sizing option as well as. So the same face I have selected and given the element size as 2 mm. You can decrease it as per your need, that but less than 2 mm is preferred, because the geometry dimension is less. So 2 mm is mostly for which can give me good results. The help of 2 mm, as well as the refinement is one option which I have added and selected this surface, 2D surface. In 2D name section, as I have discussed here, this is my inlet. So I define so this is my inlet. I will name this as inlet. This edge, entire edge, I will select with the help of this method. And I will click this here, and with the help of this I will just name right click on this and create name section, there is an option name, so I will just name it as inlet. This is my outlet, and the wall, which is this entire wall, I have named it as wall. The entire orifice, or you can just say it as venturi thing, where the converging, diverging and through angles are there. So I have named them as wall. So yeah, that's it. And if I update this mesh, it would go in setup option. As I have not made any changes, so I won't be updating. Okay, the Fluent will open it. Double precision with parallel, and will give this as process 4. So here is it. So after Fluent opening of this setup, now we will look into the methods as well as which boundary conditions I have inserted. The Fluent takes times little bit because of the model, as well as it depends on the processor of your laptop also. So this might take few minutes. Okay, this is the setup 1, where you can give the boundary conditions as well as the methods, everything, every detail, whatever the governing equations are added in this setup. So window, you can just define it. So the general section, the pressure based as well as steady time I have defined, and gravity option is not turned on because I don't want the gravitational effect right now. And the main materials in which I am going to select is water liquid and water vapor, because in this, the water liquid, I am going to allow it from the inlet side, and that I am converting into water vapor. So the two materials which are required were water liquid and water vapor. So in material section, I will just go into fluid domain. Here there is an option named as Fluent database. So coming down, there is one option named as water, water liquid, water vapor. Related to water, everything is there. H2O, right things. So yeah, here is it. Water liquid and water vapor. I will just import these things. I will say copy, and automatically it will come over here. Water liquid, water vapor and air. As air is not needed here, these options can, the air can be eliminated with the help of multi-phase domain and assigning the phase, interference phases. So yes, water vapor, water liquid, two things are added. I will just turn on this equation. Yeah, this is the basic model. The first equation, that was multiphase. If we turn on the multiphase equation, there are quite three things like volume of fluid, mixture, Eulerian. So these Eulerian and volume of fluids are related to agitators, as well as the multiphase if there are surface to surface interactions. But right now the option I am going to select is mixture. In mixture, there are two things, that are two materials, number of Eulerian phases. So I have assigned it as 2. Okay, and in the phases I have defined it as water liquid and water vapor. Water liquid is the main phase, primary phase, from which the conversion process will take place, that is from water liquid to water vapor. So water liquid, you can just edit and give the name over here, like whatever you want. So I have selecting here. As I said that you can air can be eliminated, so from this section you can eliminate air and give it as water liquid. Say OK. Vapor, this is the second phase you will get. So vapor, I have just named it water vapor, and OK. Just keep default settings like diameter and everything. So the both phases are turned on. And coming to the next one, that is phase interaction. So just go into the mass, and here there will be number of mass transfer mechanism will be 0 at the initially, but afterwards you need to turn 1, and because there are one material changes from which water liquid to water vapor, so I given this as 1. If you want water liquid to water vapor, diesel gas to diesel liquid to diesel vapor, so you can just turn it to, and you can add this in material section. But right now there are only one materials to be converted. So water liquid, I selected this water liquid to phase, that is vapor, and there will be none before. So later one you can just give this as cavitation and keep this everything same default constant. OK. Cavitation effect mechanism, surface tension is there, just keep as default as possible because we don't want to complicate anything, just a simple flow with cavitation effect. And liquid mass is there, water liquid to vapor, cavitation effect mechanism. OK. And the energy equation is turned off, by the way. You can just give, if the temperature, if you need to assign, you just can give a temperature thing. This is the main thing, the viscous model. Viscous model, in which I have assigned it as K epsilon, that is 2 equation model, and transport equations is known to be, and in K epsilon model I have given the realizable method as well as standard wall function, and just press OK. Coming to the boundary conditions, inlet, pressure inlet, just give me a second. This is the inlet, this is the outlet. So the pressure at inlet is 5 bar. So the thing I am going to convert from 5 bar to Pascal, that is from bar to Pascal I have to convert. So I will be converting in this Python software. So we'll just give the variables and convert the units. As we know that 1 bar is equal to 1 lakh pascals. So keeping in mind, we will just convert as the value can be in decimals also, so we'll be giving float term, or else like you can give, if you are sure that it will be like unit wise without any decimals, so you can give a integer that is int. So right now float input, enter the value in bar. So my b term will be float of a into 1 lakh. This is 10,000, this is 1 lakh. So here it asks for to enter the value in bar. So I will put, as I said, 1 bar is equal to 1 lakh Pascals. So 1 bar images. So it has printed that 1. So see, this is 1 lakh term. You can Google it also if you are not sure. So 1 lakh is equal to 1 lakh Pascal. So we are close to it. So right now the value initially we are giving at inlet is 5 bar. So 5 bar, I will be entering the value in bar, that is 5 bar. So it is 5 lakh Pascals. So this at inlet I will be assigning as 5 lakh. I will just copy from this one. Keep here. This is 5 lakh value. The supersonic initial gauge pressure just little bit less than this, 4,50,000 Pascals I have kept it as, and in K and epsilon assigned it as 0.02, and that is turbulent kinetic energy, and turbulent dissipation rate is 1. So okay, and the vapor should be 0. The volume fraction of vapor should be 0. Just keep in mind, if this goes 1, the entire problem will be wrong. So multiphase, the inlet vapor should be 0. Again, at outlet, the pressure at outlet I will be assigning. So here is it. The pressure at outlet is 0.9. So as I said, if you are going to assign in decimal points, you will have to assign in Python the float term. So right now it will be tested that if we are correct or not. So 0.9, yes, 90,000. You can just go on this 0.9 and you will get 90,000. So copy from this Python software and paste. Actually it was 9.5, right? No, 0.9. And that's it. Okay. So right now we have covered multiphase, that is cavitation model. Everything will be default. The surface tension would be 0 only, and cavitation model should be turned on. Later the phases in phase interaction, in that term the masses should be 2, the masses should be 1, and in phases, phase 1 should be water liquid, the phase 2 should be water vapor. Coming to the next part, viscous term, realizable K epsilon, and in boundary condition, the pressure at inlet, the pressure at outlet, the pressure at inlet be 5 lakh and the pressure at outlet be 95,000. In the methods, I assigned it as coupled method, and everything is default. Volume fraction first order upwind, turbulent kinetic first order upwind. And coming to this initialization method, if you are sure that the standard inlet temperature as well as the inlet velocity, if you do know the gauge pressure, you can just proceed with the standard application and compute from inlet. You just can give it, or else here they will ask 10 K velocity is 10 or what. The answer should be accurate here, but if you are not sure about this, you just can give it hybrid initialization and initialize it. Yes, the hybrid initialization is done. So right now the next step is proceed for iterations. In this I will be assigning 500 iterations, and yes, save to calculate. This will take some time. So yes, here we have completed the iteration 1. These are the residuals in which we can just find out K epsilon term which we have turned on, as well as continuity equations are there, x velocity, vapor pressure, vapor fraction, volume, that is volume fraction of the vapor as well as liquid. So yes, I will be closing this window and straight away I will look into the results of this. So these are the contour plots of volume fraction. I will just turn off the streamline wireframe. I will add the contour section. In this contour section I will be selecting plane 1, which is an XY plane, and yes, the density is there. So in the density section I will be adding the volume velocity. First we will be seeing velocity local. I will slightly increase to 20 and then apply. So these are the velocity. This is the velocity plot in which you can just see there is increase in velocity at the throat, and due to this just happens because of pressure difference. And right now we will be seeing the cavitation technique for which we have done the simulation by clicking the volume fraction of water vapor. So we have converted from water liquid to water vapor. So water vapor volume fraction we will be looking at. So here it should be what volume vapor volume fraction of vapor. Okay, so these are the plots, these are the bubbles. I have added the guideway just to see here how the bubbles are, how the cavitation and bubbles are forming here. And due to this the erosion takes place, as I said in previous videos, the pressure difference. And if we consider any point and if we reduce that pressure of that vapor to this vapor pressure or less than vapor pressure, then the vaporization process takes place, and this nothing but results in cavitation process. So yes, here is it. I will show you the streamlines also. Okay, in this you will clearly getting an idea of how the streamlines, the bubbles are going to form and how they are going to transport from one point to another point. You can see here the red denotes 80 around 0.8, and vapor fraction, as I said, the vapor pressure should be 0 right now in previous setup. So these are the results. You can just turn on. Yeah, this is it, and I will be explaining you more about the simulation as well as the methods, the definition, as well as I am going to explain you in this CFD by using Python somehow for unit conversion, as well as later we will be seeing much more videos on Python, as well as implementing those Python into CFD softwares. So slowly we will add up that also. So I hope you like this video and this will be helpful for your understanding. Thank you.